Greetings, everyone. So let's begin live session 4. This is the fourth week of our course, and this course is taught by Professor Sanjeev Sambhagan, and I am TAing the course. So let us solve the numericals from second assignment first. Previously, we had covered the first assignment. Now we will try to solve the rest assignments in this live session. So question 1 says that uh, number of lattice points per unit cell in a body center cubic lattice. So you are required to find how many lattice points are there in a BCC per unit cell. So we know that in BCC we are having two lattice points per unit cell because there will be 8 uh, at the corners, and those 8 will be shared among the rest of the 8, and we will be having one at the body. So in total we will be having 2 lattice points per unit cell in body centered cell. So the option D here seems to be the correct option. So we will go with option D. Now, if we move to the second question says that we are given a zinc blende crystal structure. Uh, a zinc blende is simply a FCC cubic lattice, but it has 2 atoms per unit per lattice point. Basically, it has lattice points and it has some bases. So that's why this FCC it is called zinc blende structure, and in here we will be having 2 atoms per lattice point, and we have been given the lattice spacing is 5.65 angstrom, and we are required to find the number of atoms per cubic centimeter in this zinc blende gallium arsenide. So we will simply write down the solution by saying that we are having 2 atoms per lattice point. It's that simple. So we know in FCC has 4 lattice points per unit cell. So if we simply see that there will be now 2 into 4 number of atoms, gallium arsenide atoms per unit cell. Number of gallium arsenide atoms per unit cell is equal to 2 into 4, and this gives us 8. Now we are required to find the number of atoms per cubic centimeter. So it means we need to find the volume first, and we know the lattice constant A is given by 5.65 angstrom, and we know 1 angstrom equals 10 to the power minus 10 meter. Now if we convert this into centimeter, it will simply be equal to 5.65 into 10 raised power minus 8 centimeters. So, since this is a cubic lattice, this volume will simply be equal to a cube. Now, let me just write the number of atoms per cubic centimeter will be equal to, this will be equal to, this will be equal to number of atoms divided by volume of unit cell. So here we are having number of atoms to be 8. Yes, it's 8, and the lattice constant is 5.65. It is 8 divided by 5.65 into 10 raised power minus 8 cube. So let me solve this on my calculator. It will give 5.65. It will give 8 divided by 180.36 into 10 raised power 24, or simply when I divide it by 8 divided by 180, it will give me 4.44 into 10 raised power 22 centimeter cube per centimeter cube. So we have got the answer to be equal to 4.44 into 10 raised power 22. Let's check the options, and option B here seems to be the correct one. So we will go with option B. Now let's move towards the third problem. It simply says that we are having the X-rays of wavelength 0.5 angstrom, and these X-rays undergo a second order reflection at an angle of 10 degrees from the crystal. So we are required to find the spacing between the atomic these planes in the crystal, and we have to write that in angstroms. So we will simply use Bragg's law, Bragg's law of electron diffraction, which, as taught by the professor, simply states 2d sine theta equal to n lambda. So this n here is 2, as it has been mentioned in the question that it is the second order reflection. So the wavelength here is 0.5 angstroms, and it is equal to 0.5 into 10 raised power minus 10 meters. So now we will simply write this d. This d will be given by n lambda by 2 sine theta, and theta is 10 degrees. We will simply write it to be 0.5 into 10 raised power minus 10 divided by 2 times sine of 10. Now let me calculate the values. It will simply come out to be equal to 2.88 into 10 raised power minus 10 meters. Since we need to write it in the angstroms, it will simply be equal to 2.88 angstroms. So option D seems to be the correct option, and we will select option D itself. So we have solved the first three problems. Now let's move towards the fourth problem. And fourth problem states that we have to consider a semiconductor whose energy dispersion relation, the EK relation for the conduction band, is given by E equals A plus B K minus C whole square. Yes, it's correct. A minus B. Now we know we have to find here the mean free time of the electrons in the conduction band. We know that this mean free time can be related to the mobility by a simple relation. Mobility is simply equal to mu not equal to q tau by m star, where this m star will be the effective mass in the conduction band. We have been given the value of mu and we are required to find the tau. And now m star, we know, as seen in the lectures, will simply given by the h star by d square E by dk square. And you should remember this always, that this kind of relation for the m star will hold for parabolic bands, where we are assuming that E is equal to h bar k squared. And if there are some other kinds of bands like linear, then this might not hold there. So if we now derivate this E once, it will give us dE by dk to be equal to simply 2bk minus c, 2 times b into k minus c. Now we will again derivate this with respect to k, and we will get it to be equal to 2 times b. So m star will simply be equal to h bar square by 2b. And since we have got the value of m star, we can write the mobility, we can write the mobility to be equal to mu, wait a second, mu equal to q tau by m star, where this m star we have found to be equal to in the previous slide, this is actually a wrong slide where I have written it. Let me write it here again. Mu is equal to q tau by m star, where this mu m star by q is equal to tau and m star we have found it to be h bar square by 2b mu naught times h bar square by 2b q, and this will be the relaxation time. And clearly, if we see the option C clearly matches it. Mu naught h bar square by 2bq. So we have got the answer for this problem as well. Now if we see this problem fifth, it states that the electrons are in n-doped in crystalline silicon and they suffer from scattering. It is a hypothetical situation that they are assumed to be scattered only by the lattice vibrations and only by the interaction with the impurity ions. So now we are taking a case when the temperature is very less. So what will happen to the mobility? If we increase the temperature at low temperature, I'm talking at low temperatures, if we increase the temperature, what is going to happen with the mobility? We know that, as I have already pasted it here, that at low temperature, these crystal vibrations, they will be very less. So this will be not the determining factor for the mobility at low temperature. But the scattering due to the impurity ions will be the major determining factor. So if we increase the temperature when we are moving from low temperatures and we are increasing the temperature, this electron will now spend less time in the vicinity of this impurity, and this will result in the increase in the mobility with the increase in the temperature at the low temperatures. So for us, the option D seems to be the most suitable, and we will say that the mobility will increase. Now, if we move towards the sixth problem, and this is a straightforward problem, and you all must be knowing that its answer will simply be equal to the, it will depend on the lattice constant itself. So it will simply be equal to k equal to n pi by a as derived in the lectures. So we will simply select option A. And if we move towards another problem, which is also a straightforward problem stating the uh, definition of the Brillouin zone, and we know that Brillouin zone is nothing but the region or the K space which lies in the K space, and it contains all the unique solutions for the wave functions. So we know this, that the answer should be A, and we simply write it to be A option will be the correct one. So if we now move towards another problem, here this is some good question in here. It states that we are given a 1D band structure where this Ek has been defined to be equal to h bar Vf kx. Now we are required to find the effective mass. We know that effective mass, as seen in previous slides, is given by h bar square d square E by dk square. So we see in here that if we write this linear relation, its second derivative will not exist. So what will be its effective mass? The effective mass simply in these cases, if we have a linear relation, will simply be not defined. Though there are other mechanisms like velocity that we can determine, and they can help us in governing the properties of the system, and uh, this band structure effective mass property can be bypassed in these systems. So simply in this kind of system, we will simply write the mass is not defined. So simply the answer will be B. Second derivative will not be here. So we uh, we move towards the next problem, and also you can see this kx has mod in here, and it will look like this. If we say mod of x y equal to mod of x, this is the function it will look like, and we know that derivative for this function will not exist at x equal to 0. That's also one of the reason for this having no effective mass, not defined, effective mass being not defined. So now if we move towards ninth problem, it is about the Bloch's theorem, and it deals with the periodic potential. It says that the Bloch's theorem for a periodic potential is given by psi of x plus a, where this a will be the lattice constant, after which the potential will be repeating itself and giving it a feel that it is same everywhere. So this psi of x plus a will be equal to psi of x, and it will just be the multiplied by some phase factor. exponential of iota Ka. So simply we have been given that there is some periodic potential u of x and u of x plus a is equal to u of x. So we have to represent and we have to get some equivalent form of this Bloch's theorem. This basically is simple. We will just take the uh, options and try to solve them. And let us take directly the option D, as we know that it has the general form of this. We will simply write psi of x. We will assume psi of x to be equal to u of x e to the power iota k of x. It is simple. So now let us write psi of x plus a. It will simply be equal to u of x plus a exponential of iota k x plus a. We know that u of x plus a is equal to u of x, so we can simply write it to be equal to u of x e to the power iota kx into e to the power iota ka. Now we can clearly see that this psi of x e to the power iota kx uh, can be written to be equal to psi x itself. That's the solution that we have assumed in here. So we will write it to be equal to psi of x into e to the power iota ka. So we have got the relation that we were looking for, that is psi of x plus a is some wave function psi at x with which is multiplied by some phase factor. So option D is what we started with, is the solution to this problem. Now let's move to the last problem of assignment second, and after that we will be doing assignment 3. And this problem states that we are having molybdenum that crystallizes into the body centered cubic structure, and it is having the lattice constant of 3.147, and the radius of this MO atom is given to be equal to the 1/2 of the center to center spacing of the nearest neighbor. So we are required to find the percentage of the cubic volume that these MO will occupy. So simply, let me have some water. So simply, we will draw some cube for the reference, and we will simply say that this cube is having the sides equal to A. This will be A. So if I draw this diagonal over here, this should be equal to, this is the face diagonal, this face diagonal, this face diagonal should be equal to the square root of a square plus a square, and it will simply be equal to root 2a. Now if we see, since it is a body centered cubic cell, we will be having this as our reference now, and let me draw it in another color. This will be the diagonal, body diagonal. This is the cube diagonal now, and now let us write this cube diagonal length. This cube diagonal length, since we found this to be equal to root 2a, this cube diagonal length di diagonal length will be equal to root 2a whole squared. This is a plus a whole square, and this will simply be equal to root 3a. Now we have got this diagonal, and we have been told that we have been told that this center to center spacing is this MO atom. This radius of this molybdenum atom is 1/2 of the center to center spacing of the nearest neighbors. So we will simply write the center to center nearest neighbor spacing. We know that it will be having one circle over here with which is MO atom, other here, quarter here, and quarter here. My drawing might not be perfect, but these are touching each other. So if I draw the distances will simply be equal to this center to center, this center to center, nearest neighbor spacing will simply be equal to the distance what we found, root 3 a by 2, and we have been given that the radius of MO atom is half of this. So radius of MO atom is half of this. So this will simply become root 3 a by 4. Now we will find the volume of this MO. So volume of MO will simply be given 4 by 3 pi r cube, and it will be given by 4 by 3 pi times root 3a by 4 cube, and it will simply come out to be, it will 4 and 4 will go, and root 3 will be there only, root 3 pi, and there will be a cube, and there will be just 16 left, as 1 4 will go and 3 will go with 3. So we will simply be having this volume of MO. This will be the volume of molybdenum. Now we know that the total, we have to find the total volume. So in BCC the number of atoms is 2. So the total volume will simply be equal to total volume of MO will simply be equal to that the total volume of MO inside this cube will simply be equal to number of atoms into the volume of MO. So it will simply be equal to, in BCC we will be having 2 atoms into the volume of MO. Volume came out to be equal to root 3 pi a cube, root 3 pi a cube by 4, 16. Okay, 16, yes. So this 2 will cancel out, and we will be left with root 3 pi a cube by 8. Now since we are required to find the volume in terms of the percents of the volume occupied by the whole cell, it will simply be percentage volume will simply be equal to the this VT, let us know this way, VT, the total volume divided by the volume of the cube into 100. So this simply will be equal to root 3 pi a cube divided by 8a cube into 100. Now let us simply evaluate this, and since this a cube and a cube will go, we will be left with root 3 pi root 3 into pi divided by 8, and it will come out to be approximately equal to 68.01. So we will write it to be equal to 68%. So in here, only option C is close to 68.01. So option A is, option C will be the correct option to go with. So we have solved this assignment, the assignment 2. Now let us move to the another assignment, which is assignment 3. And in here, the first problem, it states that the energy band diagram, we have been given an energy band diagram and we have been told to find the electric field. What is the general formulation for this? We have to find the electric field. Now we know that there is some relation between the applied potential, that is V, and the field. We will simply write the field with this notation E, and this E is, we know, is given by minus dV by dx, where this V is the applied potential or the voltage. Simple. So we know that this this energy band diagram energy band diagram represents C proportion. Yes, absolutely. But still, we have to solve this because others might see this video later. So let us solve this. So this energy band diagram represents the energy levels. Energy levels, energy levels of the electrons. So simply this energy is simply given by for an electron will simply be given by, let us use another slide. E will simply be given by, for electrons, E is equal to minus Q into V, where V is the applied potential. Now, we know we have written the relation for the field previously, where it was E is equal to minus dV by dx. So we can write E minus E by Q to be equal to V, and this will be replaced in the previous iteration. It will be minus d by dx of minus of E by Q. So it will simply be equal to 1 by Q d E by dx. So as rightly said by Lakshmikanta, that we will be getting the option to be equal to the proportional, it will be proportional to the slope of the energy. But here I have not written conduction band because it depends upon the reference. So if I take energy E equal to EC as the reference level, then it will simply be 1 by Q dEC by dx. So this is our field for the uh, uh, for the carriers, the electrons that they will be facing, and that it is proportional to the slope. So we will simply select option C. Now this is question second, and this question second is also somewhat conceptually uh, demanding question, and it demands some conceptuality. It is about just the Fermi-Dirac distribution. It states that we have an n-type semiconductor and we have been told to find its Fermi level. So let's get it clear that for an n-type semiconductor, the Fermi level will simply be above the mid. It will not be below the mid level. If we have the conduction band and the valence band, it will be having the mid level, and the Fermi level will always be above this mid level for the n-type semiconductor. So we have just reduced our options from 4 to 2 because near the middle of the band gap will clearly not be there because we have seen that it will be above the middle of the band gap and it will not be inside the valence band. Now we have two options left here. So one is inside the conduction band and another is the whether it is between the donor level and the conduction band. Now here is the trick because we have been told that the temperature is here 0 degrees and we know that at T sorry at T equal to 0 Kelvin. This is the simple definition that Fermi-Dirac statistics, FD statistics, it says that all the states, all the states below Fermi level, Fermi level should be filled with electrons. And we know for donors that no dopant atom could be ionized. Why? The reason is simple. The temperature is really less. It is 0 Kelvin. How will they get this energy? So no dopant atoms could be ionized due to the lack of energy. So all the donor states, all the donor states will be filled, with electrons. So what does this mean? This means that this has to be above the donor states. The Fermi level has to be above the donor states. But we know there is no talk about the degeneracy, and clearly the option D will be the best option to select because we are dealing with n-type semiconductor and the donor levels have to be completely filled with the electrons. So the Fermi level will lie somewhere between the donor level and the conduction band edge. So the option D is the correct option to go with. Now, if we see the third problem states that we are having a silicon wafer and this silicon wafer has been doped with phosphorus. This phosphorus is a pentavalent impurity and we have also doped it with boron atoms, which is trivalent impurity. So one will act as dopant and another will act as acceptor. And we have been told that the temperature is 300 degree kelvins and the carrier concentration, which is the intrinsic carrier concentration, it is given to be equal to 10 to the power 10. So we have been told that all the dopant atoms are ionized. So we have to take simply this Nd positive or Na negative to be equal to fully ionized, and we have been told to find the location of the Fermi level with respect to the conduction band edge at this temperature, which is 300 degree kelvins. And we have been given the effective density of states at the band edge as well. So we will simply see what we have been given. We have been given the acceptor and the donor impurity levels. And acceptor impurity level is simply 6 into 10 raised power 16 cubic centimeter. And donor is simply equal to 15 into, sorry, 5 into 5 into 10 raised power 6 it is. 5 into 10 raised power 16 centimeter cube. Now we can clearly see that if we find the effective doping, it will simply be equal to Na minus Nd. Na minus Nd. It will be 6 into 10 raised power 16 minus 5 into 10 raised power 16. and it will simply mean we will be having 10 to the power 16 centimeter cube effective doping, and this will be due to the acceptor atoms, because as we can clearly see, this acceptor atom is having more magnitude as compared to the donor atom. So we can clearly see that this will be equal to P, where P is equal to Na minus Nd. This is the concentration, and this concentration will be equal to 10 to the power 16 centimeter cube. Now we have been told that this is in a thermal equilibrium, and we can use the law of mass action, which states that N into P is equal to Ni squared. So if we use the relation for this Np equal to Ni squared, we can simply write this N to be equal to Ni squared by P, where we know this Ni was given to be equal to 10 to the power 10 in silicon. So this will be 10 to the power 10 whole square divided by what we got was 10 to the power 16, and it will come out to be equal to 10 to the power 20 divided by 10 to the power 16 equal to 10 to the power 4 centimeter cube. Now, why we went for this and this concentration, electron concentration, because we were told to find the Fermi level with respect to the conduction band edge. That's all. So we know, as seen in the lectures, the relation is simple. It states that the concentration, electronic concentration, is simply given by n equal to nc exponential of ef minus ec by kt, where this Nc is the effective density of states, and we know that this effective density of state value is given, and we will substitute it directly whenever required. We can take it to be on the other side. It will be N by Nc equal to exponential of Ef minus Ec by Kt. Now applying ln on both sides, applying ln on both sides, we will simply be having ln of n by nc is equal to ef minus ec by kt, or simply this ef minus ec will be equal to kt ln of n by nc, and this kt is having the value of equal to 26 milli electron volt. We will simply write it to be equal to, sorry, we will simply write it to be equal to this ef minus ec will simply be equal to 0.026 ln of n by nc, where this n we found out to be was equal to 10 to the power 4 cubic centimeter, and this nc is given to be equal to 2.82 into 10 raised power 19, 2.82 into 10 raised power 19, and let us compute this. Simply, let us compute this. 10.4 divided by 10 is equal to, so it will give us the value will be equal to 0.026 multiplied by minus 35.36. So if I multiply it by 0.026, it will simply be equal to minus 0.92 electron volts. So we have found this difference to be equal to minus 0.92 electron volts. And now let us see which option it is. Clearly it is option D. It states that the Fermi level with respect to conduction band is it is below 0.92 electron volts below the conduction band edge, the Fermi level. So now let us move towards the another problem, which is simply uh, a theoretical problem, and it states that the temperature, as the temperature increases from 0 Kelvin to some high temperature, the carrier concentration, we are required to find the carrier concentration. We are required to comment about that, and we can clearly see, as taught by the professor, that this the curve will look like as in here in the plot. The plot clearly shows the region of operation. So in this, the as we see in low temperature, there will be very less carrier. So there is some kind of freeze out here. And in as we increase the temperature and move towards the normal our room temperature, we see that it is flattening. The curve is flattened, and this is the extrinsic region. And after that, as we increase the temperature, we know that the intrinsic nature of the material will dominate, and we will be having the material to be approaching towards its intrinsic nature. So here option A is the most suitable option for this to be selected. So the there is transition from freeze out to extrinsic to intrinsic. Now let's move to the fifth problem, which states that we are given an germanium wafer which is doped with acceptor, and it is density is given by 3 times the intrinsic carrier concentration by 2. So it's 1.5 times the intrinsic carrier concentration. And we have been given some temperature T, and we are told that the all the acceptor atoms are ionized. So we are required to find the hole density at this temperature T. So it's simply can be solved by using our charge neutrality. So we know using charge neutrality, N plus Na minus will be given by P plus Nd positive. So this Na mines we have been given that the uh, all the acceptors are completely ionized and there is no donor. So this will go, and this Na minus will simply be equal to Na, as we have complete ionization. We will be simply left with N plus Na equals P. So this Na, this we know that we will be having this Na is equal to this 3 times Ni intrinsic carrier concentration by 2, and this is equal to the whole concentration. So we know the law of mass action, because that is the main main factor here, that we will be using this N into P is equal to Ni squared, and we can simply replace this N by writing it to be equal to Ni squared by P, since we are required to find the whole density. So that's why we write it in terms of P. So it will be simply equal to Ni squared by P. Ni squared by P is plus 3 by 2 Ni is equal to P. Am I correct? Yes. This is what it will look like. Yes. So it will be equal to Ni square plus 3 by 2 Ni into P is equal to P square. So it will be P square minus 3 by 2 Ni into P minus Ni square equal to 0. So this is simply a quadratic equation. We will write it to be equal to 3 by 2 plus 9 by 4 9 by 4 This is not Ni square, or this is simply Ni. This is simply Ni. This is 9 by 4 Ni squared plus 4 times Ni will give me 4 times Ni squared. It will be whole divided by 2. It will simply be equal to 3 by, here we have Ni. This will be simply equal to 3 by 2 Ni, taking 1 by 4 common, and it will become 1 by 2 and Ni. It will be 9 plus 16, which will be 25, divided by 2. It will be 3 by 2 Ni plus 5 Ni by 2. So it will be simply equal to, let us read this here. It will simply be equal to 8 Ni by 4, and we will be having it to be equal to 2 Ni. So what have we got? We have got the whole concentration to be equal to 2 times of that intrinsic carrier concentration. Now let's check the options, and the option over here, option C, is what it will look like. It will be the correct option. So we have got the answer.
Sir, in quadratic equation, there should be plus minus. Why did you use only plus?
Okay, okay, that's good question. I was thinking you should ask this. Can the concentration be negative?
No. No.
That's why I used it to be plus. I omitted it because it will be just the positive value. So we have got the value to be equal to 2 times Ni. Now let us move to the another problem, which states that there is a condition in the intrinsic bulk semiconductor when that this intrinsic Fermi level will exactly lie in the middle of the band gap, and that too at some non-zero temperature. And temperature will be non-zero. So we have been taught by the professor, and I will simply use that relation, that EFI, where this EFI is the intrinsic Fermi level, will be EC minus EG by 2 minus 3 by 4 KT 1 of Mn star by Mp star. Now, from this equation, it is clearly visible that for this intrinsic Fermi level, this Fermi level to lie exactly in the middle of some intrinsic bulk semiconductor, these masses over here, Mn and Mp, they should be equal so that we don't get this term. It is as simple as that. So if Mn star is equal to Mp star, we'll be simply left with this portion, and this portion will be gone. So clearly in here, option D is the option to go with. Now, if we move towards the next problem, and I think this might be the last problem of the session, and we will continue this assignment in the next session as well, and do the next assignment as well in that session. And it states that we have been given two semiconductors, A and B, and these two semiconductors both are having the same effective density of states at the conduction band and the valence band. Now, uh, the intrinsic carrier concentration is given in some ratio over here. Some numbers are given basically. So we have been given the band gap of A, and we have been told to find the band gap of B. And coincidentally, the band gap of A is similar to that of the silicon. So now if we simply state that conditions that we have in here, we are having the NC of A is equal to Nc, that is the effective density of states of B is equal to Nc, and Nv of A is equal to Nv of B is equal to Nv, that is the effective density of states at the valence band. So if we simply use the relation for the intrinsic carrier concentration that we saw in the lectures, we will simply have Ni is given by Nc into Nv into exponential of minus Eg by 2kT. Absolutely. So we are given the intrinsic concentrations of A and B. We will write it to be Ni of A by Ni of B to be equal to Nc and V. Since they both have these effective densities equal, they will cancel out. Minus of Eg of A by 2kT divided by exponential of minus Eg of B by 2kT. So we will simply cancel these two, and we will be simply having, let us add one slide, we will simply be having the ratio to be equal to Ni of the intrinsic carrier concentration of material A divided by the intrinsic carrier concentration of material B minus of exponential of Eg plus Eg for second material by 2kT. It is simple. Now we see that this is an exponential. We will apply 1 on both sides. So we will be getting the equation to be equal to ln of Ni by A by ln of Ni by B equal to minus Eg of A plus Eg of B by 2kT. Now multiplying and taking the Eg on the other side, since we know the Eg of A, we are required to find the Eg of B. This Eg of B will simply be equal to Eg of A plus 2kT 1 of Ni of A divided by Ni of B. Now we are left with substituting the values only. So this Eg of A is given to be equal to 1.12 electron volt, 1.12 electron volt plus 2 times, and this kT will be having equal value of 26 milli electron volt, which will be equal to 0.026 electron volts ln of Ni of A. Ni of A is 1.5 into 10 to the power 10, 1.5 into 10 to the power 10 divided by 3.2 into 10 to the power 7, 3.2 into 10 power 7. Now let us simply find the values of these two. It will simply be ln of 1.5 into give me this value to be equal to 1.12 plus 0.052 into 6.15. 6.15, that's what I got. Yes. Now let me add these values. It will simply be equal to 1.44 electron volts. This is what we got for the second problem, this second material. The second material will be having the band gap of 1.44 electron volts. Now let us see which option it is. Clearly it is option B, and we are done with this problem as well. Now, let me uh, ask you if you have any questions so that we can wind up this session and start from the eighth problem in the next session and do the rest of the assignments as well.
Sir, sixth
Okay,
question, sir. Can you repeat, sir?
sixth question. Okay, this question. So basically, this is a simple relation which you can find in the lecture notes itself. Let me show that if we look in the lecture notes itself, let us see the lecture notes. This is the relation that I am talking about. Can you see this relation? Hello?
So your slide is visible.
Okay, sorry. I'm just recording it. I'm really sorry. Basically, this relation, you can find it on the slides. It simply states that EI is given by EG. EI is equal to EG by 2 plus KT simply plus KT by 2 ln of MH by ME star by 3 to the power 2. So this is the simple relation that you will be finding in the lecture notes. And I have used this relation, just use this relation. And in here you can itself see that if this whole mass and the electron mass, they are both equal, we will be getting this intrinsic Fermi level, this Fermi level just in the middle of the band gap. That's what I was trying to show you, that this part will simply be equal to 0 because we will be left with ln of 1. Ln of 1 will simply be 0. So if we are having the whole effective mass and the electron effective mass both to be equal, then in that case we will be having the Fermi level lying exactly in the middle even if the temperature is non-zero.
Sir, got it. Got it, sir. Got it.
Okay, fine. So we can end this session. If we have no question, we can end this session now. So you can leave.
So thank you, sir.
Oh, fine. Thank you very much.